Okay, now let's go over 5 electron domains. So you see here around phosphorus, we have 5 pair of bonding electrons to fluorine. So that's 5 bonds, 5 electron groups or domains. So we call this trigonal bipyramid or trigonal bipyramidal because it's a 3D structure, but it looks like it's composed of 3 pyramids if we draw the bonds from the axial fluorine here. It looks like a series of 3 pyramids. Like that. The second line I drew is kind of funky. Let's redraw that. Okay. So these shapes have important implications for chemical reactions. So that's why we're kind of learning about it. How do these relative positions of what these bonds around the atom, how do they play a role in electronically and kind of stability of the molecule? Okay. So there's 2 different bond angles. So these bonds here, this is from what we call an axial bond to a equatorial bond. And that bond angle is 90 degrees. And then this bond here is between 2 equatorial groups. So equatorial means, you can think of equatorial as equator. So it's kind of lined up with the equator. So we call this 2 equatorial bonds. Okay? And that's 120 degrees. And then axial gets its name because it looks like, if you think of the Earth as the center black sphere there, it's parallel to the axis of how Earth rotates, which is pretty much the y-axis. If we were to define our coordinate system as the y-axis being going through the Earth, and the x-axis kind of being the horizon or the horizontal surface of the Earth itself. Okay, so any atom that has 5 domains, we can characterize it as trigonal bipyramid. Okay, we'll go over into the other classifications for these 2 below in the next few slides. Okay. If we have octahedral, that's 6 electron domains. So sulfur has 6 bonds, 6 domains. And we call this octahedral because it's because if we were to label all the sides, it represents like an octagon. Or no, sorry, it has 8 faces, I believe. So 8 triangular faces. So 4 on the top and 4 on the bottom. So that's why we call it octahedral. So it's like a tetrahedral where there's 4 triangles, but there's 2 of them, so we call it octahedral. So it's like tetrahedral times 2. And one example is sulfur hexafluoride. And in this case, all the bond angles, since there's not enough room for the angles to increase, all the bond angles are 90 degrees apart from each other. Okay, so one example is SF6. Okay, all right, let's now talk about the role of non-bonding electrons in the electron domain model. So I kind of went over some examples before, so now we're going to kind of do a recap of that. Okay, so for 4 domains, there's 2 different types. We have ammonia, 1 lone pair, we call that trigonal pyramidal, like I described above. Water, 2 lone pairs, and that's called bent. So we look at these 2 examples. We see here, the more lone pairs we put on a molecule, the more the bond angle is going to decrease, because lone pairs and orbitals, when they're not shared, they're going to occupy more space because you have now 2 electrons on a single atom, instead of electrons being shared between 2 different atoms, right? So the space it occupies, a lone pair will always occupy more space than an electron in a chemical bond. And we see here in ammonia, that bond will decrease the lone pair will decrease the typical bond angles for tetrahedral, or 109.5 to 107, and then for water even further to 104.5 degrees. Okay? All right, let's move forward here. So another example, so we could label, let's label these. This is bent, and it's trigonal pyramidal. So another example of a similar molecule is we just substitute nitrogen for phosphorus, and this is phosphine. This is called phosphine. So very similar structure. And then another bent molecule, we could draw something like this. A very weird looking molecule. As opposed to water, this molecule is very reactive. So very different properties, even though they have the same chemical shape or molecular shape. Okay, so bent, trigonal pyramidal. Now, can other atoms have similar structures to water? Does it always have to be oxygen? Yes. We can also have H2S, which is very similar to water, but it has a sulfur instead of oxygen. Okay. Now let's move on to let's go over this exercise. So we drew the Lewis structure of phosphorus trifluoride to predict the shape of this molecule. All right. So if we look at the structure, right, there's 4 electron domains. So I like to use domains, but you could use groups too. Groups might be easier to conceptualize. All right, we have 3 bonding electrons. So 3 bonding electrons. Sorry, not 3 bonding electrons. 3 bonding groups. So a single bond counts for 1 group. So we have 3 of them. So that's 3 bonding groups, and we have 1 lone pair. Electron group. Okay? So when we have a relationship of 3 to 1, the electron geometry is still going to be tetrahedral because there's 4. So electron geometry, we look at the total number of electron domains. So it's still going to be 4. So that is going to be tetrahedral. Okay? Now we look at the molecular geometry. So the molecular geometry, we have to look at the lone pairs. Okay? So since we have 1 lone pair, that will take us to trigonal pyramid or trigonal pyramidal. So that's how we determine our structure here. So the shape of the molecule is going to be trigonal pyramidal. Okay? All right. All right, now we get to the little more difficult ones. There's going to be a lot more flavors for 5 domains and 6 domains. So let's kind of broaden our horizons here. So now we have 5 domains. There's 3 types. So if we have 1 lone pair, that's called seesaw. And the way I like to visualize this is, if anyone remembers what a seesaw is, if you were a kid, you would put it on the playground. There was this play structure that you basically have 2 people sit on one end of a real long board, and then there's usually something that can balance the 2 boards in the middle, and then depending on how it goes, 1 person on the end of the board will go up, and the other person will go down. So it'll be like a perpetual up and down motion. And if you're fun, you kind of see like who can fly off their end of the board first, or you play a joke where you jump off and then the other person goes down and might hurt themselves, might hurt themselves, but usually it's all fun. Okay, so if we think about this structure in the center here, it looks like a seesaw, right? So this two areas here is how the seesaw balances, and this is the one end of the seesaw. This is the other end of the seesaw. So it looks sort of like this. Okay, so a seesaw like that, and then it can rock back and forth, up and down. So when we have lone pair like SF4, sulfur tetrafluoride, that's a seesaw shape. So we see here that there's two different bond angles. So just like we talked about pyramidal, trigonal pyramidal, bipyramidal, we see we have a 90-degree angle and then a 100-degree angle, 120-degree angle. But you notice they're going to be less than what we saw earlier because there's a lone pair there. So the lone pair forces these bonds to kind of contract and shrink, and that's why they are less than their typical bond angles. And here on the right here, we drew a kind of a pictorial representation of what the seesaw would look like in actuality. Okay. So I drew those bonds there. Those bonds technically don't exist. So those dotted lines, they don't. Well, the solid lines technically don't exist. Yeah. So this is just to represent the shape. So it looks like a seesaw. But if you think it right now, it kind of looks like a kite, doesn't it? But it's not a kite. So this is just to kind of give a different perspective. Okay, so when we have two lone pairs instead of one, we get what we call now is a T shape. So if you look to the right there, I removed the electrons for clarity. So this structure looks like a T-bone or a T shape, right? So it looks like a T. So that's why we call it T shape. So not very creative with the names here. Trying to name them based on what they actually look like so they're easier to remember. So just think, to have a T-shaped molecule, you need to have 3 bonds and 2 lone pairs. And in this case, all the bond angles are going to be less than 90 degrees because there's actually lone pairs on the central chlorine atom. So those bond angles will actually be less than 90. And usually T-shaped molecules have weird kind of elements to it, like this element here. This is what we call an interhalogen. So interhalogen, this molecule here. So this is what we call an interhalogen. So the interhalogen is basically a compound consisting of 2 different type of halogen elements, and they have some use, but we won't talk about them here. But interesting compounds, and their geometries have been well known for a long time. Okay. All right, now we have to go to one more iteration here. So we call this an interhalogen compound composed of 2 different halogen elements, halogen atoms. So it could be 2, it could be 3, but the most common ones are 2. So usually you have a compound with 2 different halogen elements in it. Okay. So now we get to 3 lone pairs. So this is another case where we have a linear molecule. So the prime example is what we call the triiodide ion, I3-. So the triiodide ion is presumed to exist and form this really dark brown, black color in solution when you do reactions with iodine. So iodine can be reduced to iodide, and then in the middle of this process, usually you form the complex ion where 3 iodine atoms come together and form a ion that's negatively charged. And it's linear because the 3 lone pairs now are spaced equally around the central iodine atom that when you look at it from the side, it looks pretty linear because the bond angles between the two terminal atoms are now exactly 180 degrees. So it doesn't matter where the lone pairs are, and that's because this distance is the prime distance for the atoms to be to reduce repulsion from neighboring electrons in the lone pair bond, in the lone pair orbitals around the central atom. Okay, so this is what we call linear. So you have linear for a 5-coordinate system here on the central atom. So iodine in the center has 5 electron domains. So 2 are bonds, 3 are lone pairs. So linear is an example of that. Okay, so now let's move on to the octahedral class of compounds. So there's 6 domains. So here, fortunately, we only have 2 types. So 6 domains. So we can get higher than 6 domains actually, but some of those compounds, not many compounds fit that criteria, so we don't really talk about them. And I won't talk about them here. So 6 domains is where we'll all we'll cover. Okay. All right, 6 domains. Okay, so 6 domains. The first type is when you have 1 lone pair. You have 1 lone pair, and then you have 5 bonds. So that's called square pyramidal. And here's another interhalogen, bromine pentafluoride. So we call it square pyramidal. That's because the 4 bonds that are kind of sitting on one plane represents a square. So it's square, but then there's another bond that's sticking out of the plane, perpendicular to the plane. And if you kind of imagine that drawing some lines there, it creates a schematic on the right there of like a house. So we call that square pyramidal because it looks like a square pyramid if we were to connect all the dots there. Okay, and then the central atom is in the center there, representing the base of the house. Okay, and then the lone pair will stick out at the bottom or top, or however you draw the molecule. So it doesn't matter how you draw it. You should just draw it equally spaced out. But what's more important is just the general shape, that you can identify the shape. So in this case, since there's a lone pair, the bonding angles are not going to be exactly 90. As we saw in octahedral, it's going to be less than 90. So the molecular geometry in this case will be square pyramidal or square pyramid. Okay, now let's move on to the last type of molecular geometry for 6 domains here. So the last one is square planar. Okay, square planar, you have 2 lone pairs, and a very good example of this is xenon tetrafluoride. So xenon is one of those noble gases that can actually form compounds with other elements. It's been observed to form compounds with other elements. And we see here that in this case we call it square planar because the 2 lone pairs are pointing away from each other on one axis, and then perpendicular to that axis is a plane composed of the 4 other bonds, the 4 other electron domains that are bonding electrons to the xenon. And as you see there, if you connect the dots there, if we were to connect these bonds here, it forms a square. And since the molecule now has no bonds in the y-axis, it's a flat molecule like trigonal planar. So if all the bonds are in the same plane, we call that planar. And in this case, when we visualize the shape here, the molecule forms a square. So that's why we call it square planar. Okay? All right, so here's a little chart that kind of depicts all the examples I went over. You see here, if we have 2 electron domains, we can have a linear compound like carbon dioxide. And then when you don't have a central atom, when there's only 2 atoms in your compound, it's all automatically linear. So like carbon monoxide and the nitrogen atom. So we can illustrate what we mean. So nitrogen looks like this, a triple bond. And then carbon monoxide is pretty much the same thing. Triple bond to C. So it's not actually neutral here. It's like that. So that's carbon monoxide. Trigonal pointer, you have trigonal pointer, and then for SO2 we saw it was bent, and then for things like O2, like in this case oxygen, you could have oxygen like this. Okay, 2, 4, 6, 8, 10, and I think 1 should be 12 actually. Oh no. Yeah, wait. Oh, I see what they're talking about. So oxygen, we usually draw it a little bit differently. So usually we represent like this. 2, 4, 6, 8. Yeah. So you see here that each oxygen atom has 3 electron bonds around it, but since it only has 2 atoms in it, it's always linear. So that's why it's always linear. Tetrahedral, we have four different cases. Tetrahedral for all bonds. Trigonal pointer for just 3 bonds, 1 lone pair. Bent for 2 bonds, 2 lone pairs. And then we can also have a linear molecule. For example, hydroxide, which looks like this. 3 bonds. But like I said, these molecules are not very stable, but you can actually draw them for certain compounds, like HF. So like HF, HBr, we just typically don't think about these as linear because there's no central atom. But you can, they all are linear if there's only 2 atoms composed in the molecule. And then we have, so we'll talk about what these letters mean here, like SP, SP2, SP3, SP3D, and then SP3D2. We'll talk about that later on. Okay? Then we have the 5-membered trigonal bipyramidal, seesaw, T-shaped, then linear, then octahedral, square pyramidal, square planar. So these are some more examples of molecules here that we gone over. All right. So the last part of this lecture, we'll talk about the difference between polar bonds and polar molecules, and then we'll move on to chapter 10. So we'll be split between chapter 9 this week and then chapter 10 for the next lecture. Okay, so I'll pick up the video in the next. I'll pick up the lecture in the next video where we talk about polarity in molecules. Okay, so I'll see everyone then.